Up to this point, we have talked about solving recurrence relations using characteristic equations, but we have constrained ourselves to homogeneous recurrence relations. What if the recurrence relation is not homogeneous and we have a g of n term here? In this case, the solution Tn is going to be of the form Tn homogeneous plus Tn particular. So this is a little bit similar to if you have taken any differential equations course with non-homogeneous differential equations, you also had to compute homogeneous and particular solutions. This is exactly the same here. So the homogeneous part is the solution to the homogeneous recurrence relation given here. Well, this is the exact same equation except for Gn term. And this here is the particular solution to this given recurrence relation. Of course, this means to be able to solve a non-homogeneous recurrence relation, you will have to come up with a particular solution. Okay, I need a particular solution. Any particular solution works here, but of course, sometimes it may not be very easy to find a particular solution. Luckily, if this here is a polynomial, we have a result for that, which is summarized here in a non-homogeneous linear recurrence relation as in equation 3. If Gn has this form, okay, s to power n, this is the exponential part, times some polynomial. Okay, so bj times n to power j. So this part is a polynomial in n, and this here is the exponential part. And this has a similarity to the general solution form where we have exponential functions, or in the repeated root case, exponential function times n squared times n cubed, etc. Here, obviously, the coefficients are real numbers. T here is a positive integer, and s here is a real number. And if this s, the base of the exponential function here, is not among the roots of the characteristic equation, okay, so if s to the power n term doesn't appear in the homogeneous solution part, then there is a particular solution of the form s to power n times this polynomial term for some pj coefficients. So you will have such a form of particular solution where the coefficients needs to be solved from the recurrence relation. On the other hand, if s is among the roots, if s is a root of the characteristic equation with multiplicity m, then there is a particular solution of this form. The only difference is this n to power m case. Okay, so here recall that the characteristic equation is r to power k minus c1 r to power k minus 1 minus c2 r to power k minus 2 dot minus ck equals 0. If s here is the root of this function, this equation, with a multiplicity of m, in my homogeneous solution, recall I would have the terms s to n, n times s to n, n squared s to n, n to power 3 s to n, up to n to power m minus 1 times s to n. In that case, I will have a particular solution of this form where you have n to power m appearing in the particular solution. Now let's see this on an example. For instance, let's say the recurrence relation is given here, and obviously due to this term, this is not a homogeneous recurrence relation. Write the characteristic equation and solve for the homogeneous part of the solution, and the characteristic roots turn out to be 2 and 3. Okay, therefore the homogeneous solution is going to be of this form, having the components 2 to n and 3 to n. And since the non-homogeneous function here is 7 to power n, and 7, you see, is not among the roots of the characteristic equation. I will have a particular solution of the form Kp times 7 to n. And by definition, particular solution is a solution. So what that means is if you plug it in this entire recurrence relation, it will satisfy it. So just do that. Plug in here, Kp times 7 to n equals 5 times Kp times 7 to n minus 1 minus 6 times Kp times 7 to n minus 2 plus, this is constant with respect to uh, irrespective of the rest of the equation, plus 7 to n. Arrange the terms, gather the terms in 7 to n minus 2 parentheses, cancel them out. What you have is 49 Kp equals 35 Kp minus 6 Kp plus 49, and simply solve this to obtain Kp as 49 over 20. Therefore, the solution is of the form, this here is the homogeneous part, and this here is the particular solution. Now, since we are not given initial conditions, we cannot find K1 and K2 here in the homogeneous part. That's not a problem. If you have the initial values, just plug them in, but only after you have the entire solution, okay? Do not try to find the coefficients here before you have the particular solution, okay? Leave that until the very end. The coefficients of the homogeneous solution, you have to leave until the very end. Okay, so in this case, 7 was not one of the characteristic roots. Let's see an example where that's not the case. It's the same equation, except instead of 7 to n, we now have 3 to n. And as you remember, 3 is one of the characteristic roots. The homogeneous solution is exactly the same. However, since 3 is among the characteristic roots and it appears in the homogeneous solution, my particular solution should be of the form Kp times n times 3 to n. And n should appear here. Okay? And if the characteristic roots were 3 and 3, and in this case, my homogeneous solution would be of the form K1 3 to n plus K2 n 3 to n. My particular solution in this case would be Kp times n squared 3 to n. Simple as that. Okay, let me erase these. And in this case, again, you do the same thing. Plug in the particular solution to your recurrence relation, right? Kp times n times 3 to n, Tn, equals 5 times Tn minus 1 minus 6 times Tn minus 2 plus 3n. Arrange the terms, and you will see that the terms with n are going to disappear. You have 15n times Kp minus 6n times Kp. That makes 9 times n times Kp, which also appears here. So they are going to cancel out, okay? Because this is satisfied for all n values, because this is a solution. So when you plug in the particular solution, if the terms with n doesn't disappear, then there's a problem, okay? You should be able to solve the Kp here, in this case, as a fixed value. It shouldn't depend on n. If it does, then you made a mistake somewhere, okay? So the terms with n disappear, and what remains is, let me see, minus 15 Kp plus 12 Kp plus 9 equals 0, which gives you Kp equals 3. Okay, and since I have this, now I can put that in the solution, and this part is the homogeneous part, and this part, as we have found Kp as 3, that is Kp times n times 3 to n. I just write this as 3 to n plus 1. because that is 3 times 3 to the power n. So this is the particular part. This is the homogeneous part. And as always, K1 and K2 are to be solved from initial values.